Hello, and welcome to this teaser presentation released in advance of the virtual IEEE Sensors Conference to be held online from the 25th to the 28th of October 2020. I'm Jamie Blanche, and I am a Research Associate at Heriot-Watt University in Edinburgh, Scotland. I'm working with the Offshore Robotics and Certification of Assets, or ORCA Hub, in partnership with the Microsense Technologies Limited and the Smart Systems Group, all located at Heriot-Watt University in Edinburgh. It's a pleasure to introduce our research, asset integrity monitoring of wind turbine blades with non-destructive radar sensing. To provide an overview of the technical challenge, our motivation has been to provide runtime asset integrity data of offshore wind farm networks with a focus on blade structural integrity, by offering an alternative to rope access teams, reducing risk to life and the asset in the challenging offshore environment. Our non-destructive, non-invasive, non-contact sensing allows for early detection of critical defects, specifically delamination and water ingress. Delamination and water ingress are inherently internal defects that are not often visible from the asset exterior. Reducing operation and maintenance downtime results in greater asset productivity. Shutting down an asset for inspection is costly, and operators tend to do so only when an asset has an externally observable defect, which is sometimes too late to mitigate at an early stage. This results in costly and time-consuming repairs. By contrast, non-contact internal structural sensing deployed by drone, for example, offers earlier warning of defect onset at a fraction of the operational cost normally associated with asset inspection and defect detection. Outlining our method, we have employed the novel application of frequency modulated continuous wave radar in the K-band for analysis of porous composite structures. We have approached this problem using patented microwave sensing methods in the K-band and applied to several use cases, with our focus on wind turbine blades for this presentation. FMCW offers some key advantages. These are low power, non-contact, non-invasive radiation of microwave energy. K-band signals have a proven high sensitivity to water, oil, and porosity. Efficient electronics offer real-time, runtime, front-end capable analysis of datasets for telemetry and further analysis. Defects and common failure modes. Wind turbine blades are subject to differing operational loads and defect types. The most common are derived from flexing of the structure during operation and structural erosion due to weather abrasion. These are manifested in cracks and internal delaminations, often resulting in saltwater ingress via sea spray in offshore conditions. Structural deformation and material loss at leading edges are also common. Specific defect types are grouped into 7 distinct categories. For this demonstration, we have focused on Type 4 defects, characterized as internal damage, not usually visible from the asset exterior. The test blade. Our test section of wind turbine blade is predominantly a composite structure of balsa, polymer, and fiberglass laminated layers. Some metal components, typically lightning conductor cables and tensioners, are also present. This structure is typical for most wind turbine types, even the largest with blade lengths of up to 90 meters. Our sample is 1.5 meters long, 0.9 meters high, and 40 centimeters at the airfoil chord, where the polymer main spar can be seen. To provide a sneak peek of our laboratory results, left is a comparison of return signal amplitudes in the frequency domain for a healthy section of wind turbine blade wooden core structure versus a section of wooden core exhibiting a Type 4 defect. The x-axis is a distance measurement from the sample, with an interfacial peak observed at bin number 5. This corresponds to a target distance of 10 centimeters from the antenna, and residual signal decay consistently lower in amplitude for an observed area of delamination or porosity within the field of view of the sensor. Right is the dynamic return signal amplitude of water into the same area of internal delamination within the wind turbine blade structure. The x-axis in this case is time, with 3 milliliters added at 3 minutes and 40 seconds into the experiment. a clear signal contrast for even trace volumes of water is visible. To provide our observational summary, we have demonstrated the increase in demand for non-destructive testing to evaluate the state of a wind turbine blade. By removing the need for personnel to operate in harsh environments far offshore, deployed FMCW, autonomous robotic platform, or embedded within the structure, provides asset inspection solutions that save time and expenditure by detecting defects earlier. The effectiveness of the sensor for surface and subsurface faults within the composite has been demonstrated. The return signal amplitude for an area which is classed as healthy against an unhealthy delaminated section of wind turbine blade has also been demonstrated. We have also seen the clear detection of 3 milliliters of water ingress when applied to a delamination defect. Further work to improve current experiments for material and defect types characterization will include multispectral sensing in the microwave and terahertz bands, where the variation in inspection frequency will inform higher resolution defect types and new measurands. Integration of the platform-agnostic FMCW sensor suite with trusted autonomous systems will allow improvement in asset management efficiency, saving costs in OPEX and CAPEX while preserving the longevity of the renewable energy asset. We invite you to view our other research outputs presented at the virtual conference. These are an evaluation of millimeter wave radar sensing for civil infrastructure, and runtime analysis of road surface conditions using non-contact microwave sensing. We thank you for watching, and we look forward to presenting our results to you in full at the virtual conference in October.